This has to be done. No. Not this one. No, not that one. Maybe this one. It has to be done. No, not that one. Let's try this. Nice and sharp. Let's try that. There you go. It's done. Welcome back to the shrine. Today we are going to fix something. This is the cover from my CNC, and when I bought it, there were two wires hanging out on the side. There was electrical tape on one of them. The other one didn't even have electrical tape. So I took it apart to investigate, and what I found is this is the top of the spindle. It's the highest part on the CNC, and this was full packed with stuff so badly that the fan blades didn't spin. They couldn't spin. It was so tightly packed with stuff. I was trying to get the CNC going. It's a 3-year project. It's still not running. I'm getting there. I'm fixing it slowly. One day, my brother, it's gonna work. But I was suspecting that this encoder was one of the culprits. So what this encoder does, it tells the computer the speed with which the spindle is running. This is also instrumental in aligning the tool. When the spindle is about to go for a tool change, it has to align to a tool. It has to align the tool to the specific clocking position, and this is the feedback mechanism. Now, this cable inside was just rattling. It was not retained in any ways. This end of the cable was completely, just like as you see it, there was a little tape here, electrical tape on the side, but this section right there, this section was completely open to the elements. So I decided to take it apart and look into it and try to figure out how can I fix it. No, I was trying to hook the encoder up to an oscilloscope and see if there's a viable signal coming out of it. And the signal was kind of gibberish, and then I realized that one of these wires right there, a green wire, is broken. So I'm suspecting that the rest of the wires might have some issues. So what I'm gonna do is replace this cable assembly. Okay, it's got 9 cables, 9 wires, and I'm gonna replace it, and then most likely replace this connector assembly too. So follow me on this project. Let's see if I can get it to run finally. Right here the cable is locked up with this glue, and you can see I removed the glue and the blue wire just jumped off. So the blue wire was broken also. So it's not only the green wire right there, but it's the blue wire too. Now the problem is I've got no idea where the blue wire came off of. It's probably this back portion here. What I wanted to do is remove this goat's nut, hot glue, you name it. We'll remove it in such a way that I'm gonna have access to the wires, but it's not gonna happen. So there's clearly 2 wires here, right there. So there's the blue wire and then the green wire here, and they were both broken. Again, I hooked this up to an oscilloscope and the signal wasn't really clean, and I took the cover off to see if the disc inside here, so this is the disc itself, so that's the actual disc that has the openings on it, and I was afraid that some of the dirt from under the fan got injected here and maybe made the disc dirty. That may be still the case, but when I started to test it, that's when I realized some of these wires are just flopping in the air. So I'm gonna have to go and clean this up, clean up properly this, and solder the wires in. I'm gonna need to solder the new wires in. So this wire has some designation here, but it was unreadable. So I just figured out the gauge. I actually reached out to the manufacturer. It's Sumtak. You can see it here. I reached out to them and they sent me a drawing for this. So it has the pinout and it also has the cable designation, and I went ahead and ordered the cable. So this is what I got. This is from Mauser Electronics. Okay, here's the part number, and this is basically I think it's 26 gauge wire, and you can see it's tightly packed. It's got 9 pairs plus ground. So this is what I'm gonna use to hook it up, and hopefully the color coding is the same or similar. All systems are up. Got a stepper motor driving the encoder, and the wires are connected to this breakout box so I can attach the channels. So what we are doing here is measuring the each channel between the ground. So this is the ground lead. This is positive ground lead, A naught, B naught, Z naught. So I'm measuring A, B, and Z channels right now. So the A is being 1, B 2, and then Z is 3. So here's the setup for the oscilloscope. So you can see I'm triggering on channel 3. Okay, so channel 3 is the Z signal, and you can see this nice long signal. And then we have channel A and channel B. So channel Z starts where channel A is. You can see they are in line, and then channel B is one quarter period shifted, so 90 degrees shifted. So those are channel A, B, and Z. And now I'm going to put it on the nod channels. So we got A naught, B naught, and Z naught, and you can see we got a nice signal on all of the channels. So the next thing is to package it up and wire up the connector, and then put it back in the machine and see if it runs. I put it together and I soldered in on the wires, okay, as you can see, but I cut it off because reasons. Okay, so here's the cable, the new cable I bought. You can see I cut the jacket off, and I'm gonna go and remove the insulation. And when I do that, you can see there's this metal shield on it, okay, and below the metal shield you can see the cables are just twisted. You see that they are in a long helical pattern, so all the cables are twisted together, okay, but they run parallel to each other. Now on machinery like this, like a CNC mill, you can have several different emitters of electromagnetic noise. Also, that can be crosstalk between the cables. So you can see that the power cables will be the white and the black. They bring in the DC voltage, and they run completely parallel to that. So if there's any fluctuation in the DC voltage line, that can appear on in the rest of the cables because they run parallel. Now here's a piece of the original cable, and you can clearly see that the pairs are braided. So it's not twisted. This one is twisted. This one is braided. And by braiding I mean that you have pairs of cables. Okay, so it's a twisted pair. So if you look at the black and white, you can see they twisted together. If you look at the pink and the red, they twisted together. The blue and the green, the orange and the yellow, they individually twisted together, and there's an amount of twisting per length. And honestly, I'm assuming that the twisting is different for the pairs. So for example, the blue and green would be twisted, 17 times on a foot, and then the yellow and orange would be twisted 13 times on a foot, so that the pitch is different. So they are trying to minimize the crosstalk between the different cables. So that's what I'm gonna do. I'm gonna go and separate this cable, basically, just separate all the bunches, and then twist the individual pairs, and then make them into a cable and terminate it that way. got it completed this far, so the new wires are soldered in, and then I twisted the individual pairs and then tied them together, and now I installed shrink tubing. I'm not sure about what to do with the ground lead here. I might just solder it to this stand, this post. So that's what I got. So here's the original cover. Okay, this cover just was installed like so. You can see that there's a cutout on this side, so that slides in like this. And then right here we had a rubber grommet, so that rubber grommet just slid in and basically prevented ingestion of debris or dust. And you can see this had some kind of strain relief on it, which is long gone. This, you know, rubber ages generally. You can see, I just look at it and it crumbles. So this is how it was done. So this rubber grommet was glued to the cover, and I didn't like that. I didn't like that there's no strain relief. I think to begin with, one of these wires broke off because there was no strain relief. So I went ahead and I 3D printed one. This is basically a copy of the original one, you can see, but I used 2mm wall thickness. I'm just comfortable with that. This one has 1.1mm wall thickness, the plastic, so I made this a little larger. I mean, it will fit on the outside. There's enough room around it, so the cover installs like so. And you can see that it's a nice fit. Okay, and then I have a piece here, a bracket that slides in here, and I can bolt it on. So with that, the encoder assembly and replacing the wire is complete. So I'm going to go to the next one, which is the connector end. This is the cover. You might remember it was real dirty and nasty before, so I went ahead and sandblasted, and then I put a couple coats of primer, a couple coats of this gray finish on it, and it looks great. I was debating for a while to reuse the original connector. This connector hooks up the encoder. It goes in from the outside like that, and it bolts on. The cover has these protrusions and they cut threads in it, so the bolts go in from the outside like so. So this implies that I need to put this together with the wires going through the hole and then soldering it on that way. So I was debating to use this guy, which is the original connector assembly, or use something like this. I have a couple of these connectors which are aerospace type. You can see that I made a bracket. So with this I could just go ahead and mount it like so. Now the problem becomes that it's open to the environment on the inside. You can see there's no cover that comes with this one, so that I would be able to put the cover on this side and cover the wires. So I decided to go with the original one, and for this one I designed a cover assembly, what you can see here. So this one just slides on, you know, from two sides. It's basically a clamshell, and then once I tighten these bolts up, it will grab on this surface and then basically hide the wires and also act as a strain relief here. So that's what I'm gonna do. Put it back together, tighten these cover bolts, put some thread locker on them, some love, and hooked it up again, wired it up. You're looking at the A0, B0, and Z0 channels. You can see you got a real nice clean signal there, and everything is parsed as it should be. The offsets are right. So now I'm gonna go and put it on the Z. And this is the B, and then this is the A, the channel A. Okay, so just swapped out the wires, and you can see the same clear signal. Okay, so both the channel A, yellow, maybe if I shut this off. Okay, both the channel A, which is the yellow, channel B is the blue, and then the Purple is a channel Z. I can also go remove the channel Z and then go just A and A naught. Okay, so now she's triggering on the channel Z, so I can go and change that. Okay, so we're gonna go and trigger on channel 1, and then you can see the signal is good. So this upper portion here, you can see this is where it turns on, goes up, comes back down. So this is channel A, and then this is channel A naught, so they perfect mirror images of each other. Just disregard all the noise that's in there. These were the original bolts that held the connector housing, and they all rusted up, and looks like they have a Phillips head and a slotted head, and you can see it's old school. It's all rusty, so I'm gonna toss them. I installed these new screws. They are stainless. Put some thread locker on it. Looks beautiful. And now it's time for these connectors. So again, these connectors will go like so, and they're gonna hook onto the wire into housing. Look at this, think of a beauty. Everything just turned out nicely. So it's almost ready to go up on the machine. Wired up, see if it works, except the fan. The fan must reside in the housing, and I also need to wire the fan. We are in the belly of the beast. This is the tool changer part. You can see that there's some room here for improvement on those wires. This is the main spindle, so I can spin the spindle here by hand, and then there's a drive motor, and here's the main drive. You can see it's offset. So this pulley here is driving that pulley with a belt, so I can spin this here, and I put a indicator up there to see how much run out that shaft has, and you can see the run out is say it's about 20 microns, so that's a metric indicator, and one division is 10 microns. So we are looking at 20 microns run out. I think that's really in the acceptable range. Just wanted to make sure that is right before I put the encoder back on, so that that shaft, this motor shaft is not bent. Just when you thought the video is over, it's not. The situation is dire. I went through all the steps of the troubleshooting that I could imagine, and the CNC mill kept showing a fairly large size metal finger. I double checked the continuity of the wires, measured the encoder on the machine while it was running, see the signals. That Z signal is missing, and you can see I took it apart again and then hooked up the encoder to the same motor. It's spinning the encoder, and I'm tapping into the channel Z right here, right on the cover. So I'm powering it from the outside with 5 volt, and I'm tapping into this channel. And you can see on the screen that the signal pops up every once in a while, so there's a bleep, but it's not continuous. Okay, if I put my probe on the Z naught channel and I'm triggering on the Z naught, you can see there's a nice and clean signal. Okay, so there's the signal. I can make it larger. Okay, so there's the signal. That's a Z naught signal. So it's a reverse or opposite of the Z. But it turns out that the CNC is not using that signal. It's using the Z signal. Now at this moment I can try hooking this up to the VFD, to the variable frequency drive, but if it's looking for a rising edge and not a falling edge, it's not going to trigger, so it's going to be the same error mode. But if I put it back on the channel Z, you can see the signal comes back on every once in a while. So what I was doing is I was just tapping on the top, see if that changes the states, you know, just lightly tapping, but nothing really helps. I was trying to wiggle these wires that I just soldered on, but it's not working. So this PCB on the top is most likely a multi-layer PCB. So it's not just the top layer and the bottom layer, but there is intermediate layers in this encoder. So here you can see the encoder while it's running with a close shot. And these are all new wires here. So if I'm wiggling them, it's not really changing the signal. There is something intrinsically in this PCB board, something that's broken. So there's two microchips on the top. I was able to get the part number for one of them. I looked it up, and it is a power supply quad comparator, and I could not get the part number for the other one. But there's otherwise a lot of passives. Down here there's a LED which is emitting light that comes up through some kind of lens here, and then on the PCB there's a pickup, and that pickup is picking up the signal from the three channels, so A, B, and Z. And I think the NOT channels, so A NOT, B NOT, and Z NOT, those are being generated by the circuit here, the logic. So it's been probably 2 weeks troubleshooting this, and I just got to the state where I can't really fix this. You know, visually there's nothing wrong with it. There's something inside the PCB, probably a broken trace, which happens. I've seen this with 3D printers before. So I reached out to the manufacturer, and they sent me the data sheet. So this is the data sheet for the old one. Here's the cover. Okay, you can see the part number is LHA 408-1024. So that's what it says here, LHE 408 and then 1024, you know, because this is a data sheet for different resolutions, so 500,000, 2,000, etc. This is the old one. This print actually dates back to '96. So they sent me a part number for the new one, and it's called IRT 320-1024-002. They said this is a drop-in replacement, so I'm going to order one, try to find one, so fingers crossed, and just go and replace the original encoder. Thanks again for tuning in. Hope you guys enjoyed the video. Hope you guys learned something. If you like the video, please give me a thumbs up, and if you like the channel, please don't forget to subscribe. See you next time. Bye.